We can now begin to talk about stage 2 of the implementation sequence. In this stage, we are attempting to reduce the coupling of the circuit diagram to make it fit more into the form of the mechanical system that we're modeling, which has no coupling or limited coupling. In particular, no coupling at the ground. We have introduced the component, the neutral ground circuit, and so we have it here. And we will use it to reduce the coupling. And this is what we do. Where we had the circuit connected to a single ground, we now give each block its own independent neutral ground. So we have G1 being the neutral ground for the first mass, and G2 being the neutral ground for the second mass, analog. And now, after we've done that, the next thing we do is to add voltmeters to measure the outputs. There's a voltmeter here and a voltmeter there on each block. And we also now identify the ammeter as measuring current is going into and out of each block. Current will always be equal and opposite, just as our force is in the mechanical system. And the ammeter measures that current. So to implement this part of the circuit, we require something like a 4-channel oscilloscope. That would be the perfect instrument. Because if you have several ammeters and voltmeters lying around, which I know most people have more than one of those, then you can use those as well. So we connect a voltmeter across C1, representing M1, and C3, which is part of the variable mass when it is on this circuit. And this voltmeter will give us the output. If you have one that can differentiate the capture signal, then you will get the voltage per second, which represents the acceleration. But the instantaneous voltage that you measure, each independent voltage point that you measure in time, represents the velocity, which is the flow variable. Similarly, the ammeter measures the current going into this block or out of this block, into this block or out of this block. So it depends upon the direction of the current as to whether this block is experiencing a force that is positive or negative. This block has its own voltmeter as well. It measures the same type of parameter, however, it is coupled in parallel to C4. So remember how the differential variable capacitor works. When you rotate the shaft, this capacitance will go from perhaps 0 to its maximum value. And in parallel to this capacitance, they add to a single capacitance. And when you rotate the shaft in the opposite direction, this now goes down to 0 at the same rate that this capacitance C4 goes up to its maximum value. And it is in parallel with capacitance C2, so we have a capacitance adding again. This is the equivalent action to a mass flow from mass 1 to mass 2 in the mechanical system. And these voltmeters And this ammeter captures the changes as they go along. And if you're using an oscilloscope, it will record this in the time domain, and you'll give waveforms that you can analyze. So a 4-channel oscilloscope would be the perfect device, or if you have a 2-channel oscilloscope, you can use it to measure one voltage in the current, or both voltages, and using another ammeter to measure the current. But the important thing we have done here is decouple these blocks by giving them each their own neutral ground connection. This model is good for evaluating the system response to mass flows. So you may not even want to include the force in all of these experiments. You may want to find out what happens when you just rotate the knob on the differential variable capacitor to move the equivalent mass from here to there and from there to there, back and forth. The ammeter will show if any voltages or currents should just show up without there being an input current. If currents show up from the rotation of the variable capacitor knob, and that means that the mass flow will be generating forces in the system.